Introduction, upbeat background music, visuals of light waves, sensors, and quantum particles. Host, welcome to Aquamanati, where we dive deep into the fascinating world of science and technology. Today, we are exploring the cutting-edge realms of classical and quantum sensing. From understanding the noise that plagues classical measurements to the mind-bending principles of quantum detection, we'll uncover how scientists push the boundaries of precision. Whether you are a physics enthusiast or just curious about how we measure the world around us, this video is for you. Let's get started. 1. Classical sensing involves measuring physical quantities like light, sound, or magnetic fields using traditional methods. A key example is photo detection, where light is converted into electrical signals using devices like photodiodes or photomultiplier tubes. How it works: when photons strike a photosensitive material, they generate electron-hole pairs, creating a measurable current. Limitations: classical detectors are limited by their inability to resolve individual photons at very low light levels. They also suffer from noise, which we'll discuss next. 2. Classical noise. Noise is the random fluctuation that obscures the signal in any measurement system. In classical sensing, there are several types of noise: Johnson noise, thermal noise, caused by the random motion of electrons in a conductor. It depends on temperature and resistance, and is described by the formula Vrms equals 4 kBTR delta F. Vrms equals 4 kBTR delta F, where kB is Boltzmann's constant, Tt is temperature, Rr is resistance, and delta F is bandwidth. Telegraph noise occurs in nanoscale devices due to random switching between two states, often caused by defects or impurities. Flicker noise, 1F noise, dominates at low frequencies and is common in electronic components. Its power spectral density scales inversely with frequency. These noise sources set the sensitivity limits of classical measurements. 3. Sensitivity of classical measurements. The sensitivity of a measurement system is determined by how well it can distinguish a signal from noise. Two key concepts help quantify this. Classical Fisher information measures the amount of information a measurement provides about a parameter. It is defined as I, theta, equals A, partial differential theta ln p, x divides theta, 2, I, theta, equals A, partial differential theta ln p, x divides theta, 2, where p, x divides theta, p, x divides theta, is the probability distribution of the measurement outcome xx given the parameter theta. Kramer-Rao bound provides the lower bound on the variance of any unbiased estimator of a parameter. Var theta caret is greater than or equal to 1 I theta. Var theta caret is greater than or equal to I theta. 1. This bound tells us the best possible precision achievable with a given measurement setup. 4. Quantum measurements. Quantum measurements are fundamentally different from classical ones due to the probabilistic nature of quantum mechanics. Key types include projective, orthogonal measurements. The system is projected into one of its eigenstates. For example, measuring the spin of an electron along the z-axis collapses its state to either spin up or spin down. Approximate, non-orthogonal measurements. These provide partial information and are less disruptive. They are used in quantum communication and cryptography. Weak continuous measurements. These involve gently probing a system over time, minimizing disturbance. They are used in quantum feedback control. Quantum measurements are governed by error-disturbance relations, which state that precise measurement of one observable increases the disturbance of another, e.g., Heisenberg's uncertainty principle. 5. States of light. Light can exist in various quantum states, each with unique properties. Quark states, states with a definite number of photons. For example, a single photon state divides 1-1. Coherent states, the closest quantum analogues to classical light waves. They are eigenstates of the annihilation operator and have well-defined phase and amplitude. Squeezed states. These reduce noise in one property, e.g., amplitude, at the expense of increasing noise in another, e.g., phase. They are used in precision measurements like gravitational wave detection. To characterize these states, we use quantum tomography, reconstructs the quantum state from a set of measurements. Wiener quasi-probability distribution, a phase space representation of quantum states. P-distribution, used in quantum optics to describe the statistics of light. Husimi Q function, a smooth version of the Wiener function, always non-negative. 6. Quantum photo detection. Quantum photo detection involves measuring light at the single photon level. Key concepts include square law detectors, measure light intensity, I proportional divides A divides 2, I proportional divides A divides 2, where E is the electric field. Linear detectors measure the quadratures of light, XX and PP, which correspond to the amplitude and phase of the electric field. These detectors are essential for applications like quantum key distribution and single photon imaging. 7. Quantum Cramer-Rao bound. The quantum Cramer-Rao bound extends the classical version to quantum systems. It provides the ultimate limit on the precision of parameter estimation in quantum measurements. The bound is given by var theta caret is greater than or equal to 1 IQ theta var theta caret is greater than or equal to IQ theta 1, where IQ theta is the quantum Fisher information, which depends on the quantum state and its sensitivity to changes in the parameter theta. 8. Single photon based sensing applications. Single photon detectors are used in radar for high resolution 3D imaging, quantum imaging to capture images in extremely low light conditions, quantum communication for secure data transmission using single photons. 9. Entanglement based sensing applications. Entangled states allow for measurements beyond classical limits. Applications include quantum metrology, enhancing the precision of clocks, sensors, and interferometers. Gravitational wave detection, using squeezed states to reduce noise in LIGO detectors. Quantum radar, detecting stealth objects with entangled photons. 10. Atomic and solid-state spin-based sensing. These techniques use the quantum properties of atoms or solid-state defects, like nitrogen vacancy centers in diamond, for sensing. Gravimetry, measuring tiny changes in gravitational fields for geological exploration. Magnetometry, detecting weak magnetic fields for medical imaging, e.g., MRI, or material characterization. Quantum computing, using spins as qubits for quantum information processing. Conclusion. And there you have it, a whirlwind tour of classical and quantum sensing. From the noise that limits classical systems to the mind-bending possibilities of quantum measurements, we've seen how science is pushing the boundaries of what we can detect and measure. If you enjoyed this video, don't forget to like, subscribe, and hit that notification bell for more deep dives into the world of science. Thanks for watching, and I'll see you in the next episode of Aquamanati.